Last year, NASA launched a spacecraft not to Mars, not to Saturn, but to a frozen moon that most people barely think about. A tiny world orbiting Jupiter, locked under ice with no sunlight, no air, and no obvious reason to expect anything living. So, why are scientists betting on it? Why spend billions of dollars and wait for 6 years just to fly past it over and over again? Because beneath that thick shell of ice, Europa might be hiding something big, not cities, not civilizations, but something even more important: life. The kind of life that didn't start here, that never needed Earth, the kind that might prove we're not alone, not in theory, not someday, but right now. But here's where it gets strange. While that spacecraft is on its way, NASA's doing something that seems completely unrelated. Building underwater robots. Not for Europa, for Earth. For our own oceans. And it's not a distraction. It's the plan. Because before you can explore an alien ocean, you better learn how to survive in one. And down in the crushing darkness beneath our own waves is where this story actually begins. Europa isn't the flashiest moon out there. It doesn't have rings like Saturn, or storms like Jupiter, or volcanoes like Io. From a distance, it just looks like a smooth ball of ice with reddish cracks running across it. Quiet, frozen, and almost boring. But that's just on the surface. Underneath that icy crust, which scientists think is around 15 to 25 kilometers thick, there's something that completely changes the story. A liquid ocean. Not a frozen lake. Not a puddle trapped between rocks. An actual global ocean that may be up to 100 kilometers deep, stretching across the entire moon. To put that in perspective, that's more water than all the oceans on Earth combined. Trapped beneath a solid layer of ice, kept from freezing all the way through by heat coming from inside. But here's the catch. This moon is over 600 million kilometers away from the sun. It doesn't get much light, and it sure doesn't get much warmth. So, how is there liquid water? The answer is friction. As Europa orbits Jupiter, it gets pulled and squeezed by the planet's gravity. That constant tug of war generates heat deep inside, like how bending a paperclip over and over makes it hot. Over time, that heat builds up, and it's just enough to keep the ocean beneath the ice from freezing solid. This isn't just a guess, we've seen hints. In 2012 and again in 2016, telescopes detected plumes of water vapor shooting out from Europa's surface, like geysers blasting into space. It wasn't constant and it wasn't everywhere, but it was enough to suggest something was going on beneath the ice. Something moving, something active. And that's why Europa matters. Because when you have liquid water, internal heat, and chemical interactions between rock and ocean, you suddenly have the three basic things that life, as we know it, needs to get started. No sunlight, no plants, just heat, water, and chemistry. Exactly the same conditions we've already found at the bottom of Earth's oceans, near volcanic vents where strange organisms live in total darkness. So now, the question changes. It's no longer, could life survive on Europa? It becomes, if Earth wasn't the only place with the right ingredients, why would life only show up here? For a long time, scientists thought life needed sunlight. Plants use it. Animals eat the plants. And everything on Earth, in some way, depends on the sun. So naturally, the idea of finding life somewhere cold, dark, and buried under kilometers of ice didn't sound promising. Then we found hydrothermal vents. At the bottom of Earth's oceans, in places where sunlight has never reached, cracks in the seafloor release hot, chemical-rich fluids from deep inside the planet. The pressure is enough to crush a submarine. The water is near boiling, and yet somehow it's full of life. There are strange bacteria down there that don't use sunlight at all. Instead, they use a process called chemosynthesis, turning chemical energy from things like hydrogen sulfide into fuel. No photosynthesis, no sunlight, no plants, just heat and chemicals. And around these bacteria, whole ecosystems exist. Tube worms, blind shrimp, weird crustaceans that have never seen light. This was a game changer. Because if life can exist there, without sunlight, without oxygen, without anything we usually associate with living, then suddenly, places like Europa don't seem so impossible. In fact, Europa might have exactly what those creatures need. A salty ocean, a rocky seafloor, internal heat from tidal forces, and if it has hydrothermal vents like Earth's, even better. That could create a constant supply of energy and nutrients, a food chain that starts with chemistry instead of sunlight. We don't know for sure what's down there. It could be nothing. A dead ocean, still and sterile. But based on what we've seen on Earth, it's not crazy to think Europa might have some form of microbial life. Maybe something clinging to vents, floating in the dark, or even just drifting in warm pockets of water under the ice. And this isn't just speculation. These are the kinds of places NASA is preparing to explore. Because if we find life on Europa, even simple life like bacteria, it means life didn't need Earth to start. It didn't need our sunlight, our air, or our special conditions. It means life might be something the universe just does, whenever and wherever the conditions are right. And that changes everything. So we've got a frozen moon with more water than Earth, internal heat and signs of geological activity. We've got cracks that leak vapor into space, and a surface that looks like it's constantly being reshaped from below. The signs are there. The question is, what do we do about it? NASA already answered that. In October 2024, a spacecraft called Europa Clipper lifted off aboard a Falcon Heavy rocket. No humans on board, no lander, just a massive, heavily shielded machine built to answer one of the most important questions in science. Is Europa a place where life could exist? And this isn't just a quick flyby like we've done before. This is a dedicated, multi-year mission with one job. Get as close to Europa as possible, as often as possible, and collect data that tells us what's really going on beneath that ice. Europa Clipper is now making its way through the solar system. It's using a series of gravitational slingshots, first from Mars, then Earth, to build up enough speed to reach Jupiter with the right trajectory. No wasted fuel, no unnecessary risks, just calculated physics, perfectly timed to the day. If all goes to plan, it'll arrive in April 2030. Once there, it won't orbit Europa itself. Instead, it'll orbit Jupiter and perform 49 close flybys of Europa over the span of 4 years. By orbiting Jupiter, some passes will bring it within 25 kilometers of the surface, closer than most commercial airplanes fly above Earth. That's about as close as we can get without crashing into the ice. And during each pass, Clipper will be scanning, probing, and listening. On board, it's carrying a full suite of instruments, not random tools, but purpose-built systems for this exact environment. There's Reason, the radar system that can peer through the ice and map what's beneath. Not just the thickness, but the structure. Are there layers? Pockets of liquid? Are there places where the ocean comes close to the surface? Then there's the Europa Thermal Emission Imaging System, ETHEMIS. It will detect heat patterns, looking for warmer areas that might hint at plumes or subsurface lakes. If there's movement under the ice, this thing will see it. Clipper also carries a magnetometer, not for navigation, but to measure how Europa's magnetic field is being distorted as it moves through Jupiter's intense radiation belts. Why does that matter? Because the way the magnetic field bends and shifts tells us how deep and salty the ocean is, and whether it's in contact with the rocky seafloor. That's critical, because if rock and water are interacting, it creates energy, chemistry, and maybe even life. And there's more. Spectrometers that can scan the surface for signs of salts, organics, or other complex molecules. A dust analyzer that captures tiny particles from plumes if they exist. Cameras that will take high-resolution images of Europa's surface in more detail than we've ever seen before, to find cracks, ridges, chaos terrains, and maybe even openings that connect to the ocean below. But, as advanced as it is, Clipper isn't going to tell us if life is there. It's not designed to land, dig, or sample. Its job is to scout, to narrow the search, to point us to the exact places where a future mission could go in for the real test. And that's important, because landing on Europa is incredibly difficult. The surface is unpredictable. The radiation is extreme, hundreds of times more than what we get on Earth. Any electronics exposed for too long will fry. There's no atmosphere to slow a descent, no GPS, no easy terrain. So, before we risk putting a lander there, we need to know exactly where to go. Not just somewhere interesting, somewhere safe enough to land, thin enough to melt through, and promising enough that we're not drilling into nothing. Europa Clipper is how we find that place. And even now, while it's still years from arrival, the data it's designed to collect is already shaping what comes next. The cryobots, the submarines, and the future missions that will try to go beyond the ice. Because this isn't just about looking, it's about building the roadmap, and that starts with the mission already in flight. If you told someone that the key to finding life on another planet was hiding in our own oceans, they might laugh. But that's exactly what NASA's been betting on. Quietly, methodically, for years. While Europa Clipper makes its way through deep space, something just as important has been happening down here, under our own waves. This part of the mission doesn't get headlines. It doesn't have a countdown clock or dramatic launch footage. But without it, Europa Clipper would be flying blind. Because before you explore an alien ocean, you need to understand how to survive in one, and Earth just happens to have the perfect training ground. Cold, dark, pressurized, unpredictable, and still mostly unexplored. NASA has known this for a while. That's why they've been working with NOAA, building strange-looking robots and sending them into places most people will never see. Not to find fish or coral reefs, but to test exactly what it takes to survive in the kind of conditions we expect on Europa. Start with Bruy, the buoyant rover for under-ice exploration. It's not some futuristic drone or shiny lander. It's a robot built to hang upside down from the underside of thick ice and crawl beneath it. No wheels, no treads, no solar panels, just sensors, insulation, and a design that's meant to last where sunlight can't reach and communications barely get through. It's already been tested in Antarctica and frozen lakes in Alaska, because those places look and feel a lot like what we'll face on Europa. Then there's Subsea, a project that targets the seafloor directly, especially hydrothermal vents. These aren't friendly environments. The water is near boiling, the pressure can crush steel, and the chemistry is toxic to most known life. But that's the point. If we want to explore Europa's ocean, we need to know what it's like to send machines into a place that fights back. NASA and NOAA have used ROVs, remotely operated vehicles, to dive into these deep zones, where the light disappears completely and alien-looking microbes feed off chemical energy. They're studying not just the life forms, but the environment itself. How the chemistry works, what the heat sources look like, and what the geology tells us about the interaction between water and rock. It's a direct Earth-based mirror of what we think is happening under Europa's ice. But it's not just about the big stuff. There's also Ice Node, a sensor package designed to sit quietly under Antarctic ice for months, maybe even years, and just listen. No flashy movement, no cameras, just slow, continuous monitoring of temperature, salinity, melt rates, and pressure. It's not the kind of thing that makes headlines, but it's exactly what we'd need to do on Europa. Drop something in, walk away, and hope it survives long enough to talk back. Add to that the swim bots, sensing with independent micro-swimmers. These are like robotic fish, each one the size of your hand, designed to scatter, move independently, and collect data from different parts of the water. Instead of sending one giant sub, the idea is to send dozens of tiny explorers and let them fan out. No pilot, no radio control, just pure autonomy. like sending out a robotic school of fish to map an alien sea and orbiting high above Earth. There's SWOT, the Surface Water and Ocean Topography Satellite. From 857 kilometers up, it maps Earth's oceans, rivers, and lakes with insane precision. Not to watch the weather, but to detect even the smallest changes in sea level, current patterns, and heat distribution. The kind of data that lets us understand the language of water. The same kind of language we'll need to interpret once we start seeing Europa's ocean. Here's the thing. None of this tech is built just for Earth. These tools are dual purpose. Every deployment, every test dive, every sensor log is data for two worlds, ours and theirs. Every mistake made under the sea is a mistake we don't have to make 628 million kilometers away. Because you only get one shot on Europa. There's no fixing it if it breaks. There's no reboot button if the pressure cracks the hull. That's why these missions aren't just practice. They're rehearsal for the real thing, in conditions that fight back just as hard as Europa will. It's not glamorous, there are no astronauts. Just machines drifting in darkness, waiting for signals, learning how to survive. But that's exactly what the future demands. Because if we ever want to know what's hiding beneath Europa's crust, we need to build machines that don't just work in theory. They work in silence, in pressure, in total isolation. And we're getting there. Slowly but surely, one frozen lake, one deep vent, one submerged robot at a time. Let's say it actually happens. The cryobot makes it through the ice. The submersible deploys into Europa's ocean. The instruments detect something unexpected, a cluster of cells, a trace of metabolism, or a molecule that doesn't belong. Maybe it's a flicker of motion caught on camera. Maybe it's just chemical signatures that scream, "This isn't geology anymore." What then? What does it actually mean if we find life? Not fossils, not hints, but life, moving, reacting, existing right now, in real time, on a moon that spent billions of years locked beneath ice. First, we'd have to be absolutely sure. The data would be picked apart by thousands of scientists across the world, not just for days, but for years. Every reading would be reanalyzed, reprocessed, rechecked for contamination. Because the claim wouldn't just be, "We found something interesting," it would be the single most important biological discovery in human history. It would mean that life didn't need Earth to happen. That it didn't need sunlight, forests, oxygen, or anything we thought was essential. That all it really needed was water, energy, and chemistry, and maybe time. And that flips everything. Because it would mean Earth isn't special. That biology might not be rare or fragile or unique. It might be common. It might be a natural part of how the universe works, not some freak accident that only happened here. You'd have to start asking new questions. Fast. If life exists on Europa, where else might it be? Could Titan have it too, in its methane lakes? What about Enceladus, with its plumes and subsurface ocean? What about exoplanets? What about rogue planets drifting between stars? If biology doesn't need sunshine, then the rules we've been using to search for life have been too narrow. And suddenly, the universe goes from feeling empty to full of possibilities. And then there's the deeper side of it. If life happened more than once, if it started independently in two separate places, then the odds are that it's happened many times. That life is more like a feature of the universe than a one-off miracle. And that we, as a species, aren't the beginning of something, but just another branch on a much older, much larger tree. It wouldn't matter if the organisms were microbes. It wouldn't matter if they were simple or strange or barely alive. Their mere existence would mean we're not alone in the way we thought we were. Not spiritually, not biologically, not even statistically. And the more you think about that, the more everything starts to shift. It changes how we think about evolution, about consciousness, about the future of life itself. It forces every field, biology, philosophy, religion, ethics, to rethink its foundations. Would we try to bring a sample back? Would we be allowed to? What if that life is fragile? What if it's ancient? What if we're the ones introducing danger just by showing up? And more importantly, what if it's intelligent, just in a way we don't yet understand? Because here's the thing, life that evolved independently might not look, behave, or think like anything we've ever seen. It might not have a nervous system. It might not have eyes or language or bones. But that doesn't mean it's unaware. And if it's aware, even at the smallest level, we're no longer exploring. We're encountering. That's why so much care goes into these missions. Why the sterilization is so intense. Why every robot has to be built like it's entering a sacred place. Because for all we know it is. And maybe the biggest shift wouldn't be scientific at all. Maybe it would be emotional. Because for the first time, the idea that life exists elsewhere wouldn't be a theory. It would be real, confirmed, alive, and the stars would feel less distant. We've spent centuries asking if we're alone. Europa might finally give us an answer. Here's the part most people miss. This isn't a dream. It's not some far-off vision of the future wrapped in science fiction. The search for life on Europa isn't happening one day. It's already happening right now. The Europa Clipper is in flight. That's not speculation. That's a reality. It launched last year. The course is set. The mission is active. Right now, it's silently coasting through the solar system, a 6-year journey that will end with a spacecraft orbiting Jupiter and flying closer to Europa than anything before it. That alone should change how we see the timeline. This isn't an idea stuck in development. It's on the move. Teams are working every day on instrument calibration, flight data, navigation tweaks, also that when it finally reaches Europa in 2030, it'll be ready to map the surface, scan the ice, detect plumes, measure heat, and find the right spot for the next step. But while that's happening in space, something just as important is happening on Earth. NASA and its partners aren't waiting for Clipper to finish its job. They're building the next generation of tools now. The cryobots, the submersibles, the swarm bots, the power systems that can survive without repair. The sterilization protocols to prevent contamination. Every part of the future Europa mission is being shaped in real time. Not years from now, but today. In fact, you could argue the mission to Europa started long before the launch. It started in the Arctic, where Bruy was rolled beneath Antarctic ice. It started in deep-sea hydrothermal vents, where subsea gathered chemical data from environments that look nothing like the surface of Earth. It started when NASA looked at the bottom of our ocean and said, "This is what Europa will feel like." That's what makes the timing so important. Because for the first time in history, everything is lining up. We have the spacecraft. We have the target. We have the tech. We have the Earth-based training grounds. We're not just talking about looking for life anymore. We're actively building the system to find it. And the world is watching more closely than ever. With every plume detected, with every new trace of subsurface heat, interest builds, not just among scientists, but across governments, institutions, and even private companies. Because finding life off Earth isn't just about curiosity anymore. It's about legacy. It's about making history. There's also an urgency we don't talk about much. Europa is dynamic. It changes. Plumes open and close. Surface cracks shift. The radiation environment gets worse. Waiting too long could mean missing a critical window. The moment when something was detectable, reachable, or active. Missions take decades to plan. If we lose this chance, the next one might not happen for another generation. That's why this moment matters. Right now, the pieces are in motion. Scientists who spent their careers arguing that Europa could host life are finally getting the tools to find out. Engineers who sketched designs for ice-penetrating probes years ago are now building them. Test dives aren't concepts anymore. They're happening under Arctic ice, on the ocean floor, and in clean rooms that are sterilizing components for deep space conditions. It's not just happening fast, It's happening right on time. And when Europa Clipper begins sending back detailed maps, radiation readings, and ice-penetrating scans, all that Earth-based work will kick into high gear. We'll know where to land, what to build next, where the ice is thinnest, where the energy is concentrated, and where to look when we finally decide to go in. So, yes, it matters now. Because the future we've been waiting for isn't some distant idea floating in imagination. It's en route. We've always looked to the skies for answers. We send telescopes to the edges of the universe, probes to distant planets, and robots to moons we can barely see with the naked eye. But maybe we've been missing something. Because while we've been busy chasing galaxies and dreaming about alien life, we've only scratched the surface of a world that's been here the whole time. The one under our own oceans. And that's not just poetic, it's practical. Everything we hope to do on Europa, every scan, every dive, every search for life, we've been learning how to do by studying Earth. Quietly, carefully, piece by piece. Not in sci-fi labs, but in dark waters filled with pressure, chemistry, and life that doesn't care about our rules. We want to explore an alien ocean. Well, we have one. Right here. And what it's teaching us is bigger than most people realize. It's teaching us that life doesn't need comfort, that it doesn't care about the sun, that it adapts, evolves, and survives in places we used to think were impossible. The vents, the bacteria, the robotic dives, they're not side projects. They're the closest thing we have to a guidebook for what might be waiting beneath Europa's crust. The next time we talk about space exploration, it won't just be about launch dates or orbits. It'll be about ecosystems in darkness, about life powered by chemicals, not starlight, about machines crawling through alien seas that no human has ever seen, and yet somehow feel familiar. Because the deepest clues about life beyond Earth, they were never light years away. They were hiding in the one place we rarely look, beneath us. So as Europa Clipper sails through space and our ocean robots keep diving into the unknown, we're not just preparing to visit another world. We're finally starting to understand this one. And maybe, just maybe, that's what will make all the difference when we get there.